Welcome. We are looking at phase field equations. We started with the classical diffusion equation, we derived the Cahn-Hilliard equation, we found that Cahn-Hilliard equation is a non-linear partial differential equation, which is a modified diffusion equation. Okay. The modification being that classical diffusion equation has on the right hand side del squared C, the Cahn-Hilliard equation added a del power 4 C to the diffusion equation. So we had the equation like dou C by dou T equal to sum alpha del squared C, this is like the classical diffusion equation. So we found that dou C by dou T equal to alpha del squared C minus some beta del power 4 C is the Cahn-Hilliard equation. Now if you look at the other case, so this Cahn-Hilliard equation, so this is Cahn-Hilliard and this is derived with spinodal decomposition in mind. So this is classical diffusion equation. The difference between the two equations being in this case that if you have any compositional heterogeneities, they will all be evened out. In this case, if you have any compositional heterogeneities, they tend to grow with time. So that was the difference. Now when we were discussing spinodal, we also talked about what is known as order disorder. In fact, we said that if you just do not add this term and just make this alpha to be negative and try to solve classical diffusion equation, you get a solution which is for order systems. So what is this ordering and how do we model? So that is what we want to do in this lecture. Ordering is over and above the crystalline order. So the simplest way to explain it is to take a particular ordered system which is known as B2 ordered and it happens in nickel aluminum system. Okay. So if you take nickel aluminum equal atomic percent, about 50 nickel and 50 aluminum, then if you go look at the phase diagram, you will see that nickel aluminum forms a structure which is cubic. Okay. Now when you have cubic and both nickel and aluminum are FCC, but nickel aluminum NiAl has a structure which is known as B2, which is ordered BCC. Okay. Now what do we mean by ordered BCC? If suppose you take any system and suppose if it is BCC and if you take two types of atoms, okay, say red atoms and blue atoms. Right, I have say red atoms and I have blue atoms. Okay. So this is crystalline in the sense that there are specific lattice positions, the 8 cube corners. So I have missed one, let me, right, 8 cube corners and there is one body centered position and all these are randomly occupied. Okay. So any site can be occupied either by red or by blue. But when we say ordered BCC, what happens is that the atoms have a specific preference. For example, the red atoms occupy only the body centered position and the blue atoms occupy the cube corners. So this is one atom, that is one atom, that is why so it is 50-50. So when you are it could be the other way, the vice versa. Okay. So this is one variant of ordering, it is called. There could be the second variant where, because see the body centered and the cube corner are arbitrary. Okay. So it can so happen that from somewhere else, if you are forming these ordered structures, you will see that the cube corners are all occupied by red and body center is occupied by blue. Okay. So these two are known as ordered. So when we say ordered BCC, we mean that BCC itself is crystal structure. So that is an ordered structure, there is a lattice position, with each lattice position there is a motif associated with it and it forms a crystal. But when we say ordered BCC, over and above the crystalline order, there is a specific preference for atoms. specifically in this case for example, nickel atoms let us say are red, they prefer to be surrounded by aluminum atoms, right, and aluminum atoms like to be surrounded by nickel atoms. So, if you have a lattice, I mean if this is getting repeated, you will see that the nearest neighbors of all aluminum atoms will be nickels, nearest neighbors of all nickel atoms will be aluminum. Why does that happen? In the case of spinodal, it happened when omega is greater than 0 and omega is nothing but at some level EAB minus half EAA plus EBB. This is positive, meaning that EAB had higher energy as compared to average EABB. So, every time you break an AB bond and make AABB bonds, if you broke two AB bonds and instead made EAABB bonds, you will gain energy. That is why the system underwent spinodal. In the case of ordering, omega is less than 0, which means EAB minus half EAA plus EBB is negative. That means, every time you take AABB bonds, break them and make an AB bond, you gain energy. That is the reason why the system undergoes ordering. Now, when the system undergoes ordering, suppose if I decide to take the crystal, okay, let me take a system, okay. Now, let us say that I look at regions, okay. Now, the each point that I am considering now is not a lattice point, but a collection of several maybe hundreds of lattice points, say unit cells, say. Now, this could be a region in which the red atom was at the center. So, I will mark that by a red arrow. This could be another region with a red in the center, but somewhere else in the system you might get to a place where it is the blue atoms which is at the center. These are known as domains, okay, because as you can see I am using this symbol of arrow to draw your attention to magnetic domains that you would see in ferromagnetic crystals, okay. So, it is something very similar to that. So, you see something similar. So, you will see a region where the two ordered domains, in between them you will see a domain wall, where you will see that the body centered atoms being occupied by blue here and by red here. So, when you form this region, those unit cells will have unlike neighbors. So, that is like the interface and that has higher energy. The most important difference between this and the spinodal decomposition is that spinodal decomposition was described using composition, and composition is a conserved variable. What do we mean by that? If you take the integral of composition over your entire system and differentiate it with respect to time, that should be 0, because integral C dx is some C naught which is a constant, with time it does not change. On the other hand, when you have this kind of ordered domains, it is possible that these also change in such a way that the blue atom comes to the center, this boundary moves and then everything becomes. In other words, the order parameter here, let us call it as phi, okay, and like C goes from 0 to 1, phi I can say this is 0, this is 1. So, when you go across, phi goes like this. Okay, I can say that the regions where red atoms are at the center are denoted by phi equal to 0, and where blue atoms are at the center is denoted by phi equal to 1. Okay, these two coexist means that I can define a function phi, which is again let us say that f of phi, let me call f0 of phi is some a phi squared into 1 minus phi whole squared. So, it also has, so it has a minima associated with this, it has a minima associated with that phase. Again symmetric and with 0.5 in the middle, and these two are at the same value. So, this is what I assume. And there is this region where the blue atom to red atom shift takes place, and that is the region where the order parameter changes from this to this. So, for that region there is an energy associated, that I will give in terms of. So, if I write a free energy functional which is integral f dV, where f is nothing but f 0 of phi plus k del phi squared dV. I can take the variational derivative of this functional with respect to the phi parameter. So, I will get the chemical potential. Okay. So, del some mu. In the case of Cahn-Hilliard equation, the flux is proportional to gradients in chemical potential, and there was mass conservation that was included, but here there is no conservation. At the beginning you might have half of them to be having red atoms at the center, and towards the end of the simulation maybe everything has become blue at the center or everything has become red at the center, either can happen. So, there is no conservation law. So, in this case we say that the order parameter phi evolves in such a way that the chemical potential that you calculate using this becomes same everywhere. So, that is basically the constitutive law, and this is known as the Allen-Cahn equation. And in fact, for the case that we have written, so let us write this equation, dou phi by dou t minus L, mu is nothing but dou f 0 by dou phi, right, minus 2 kappa del squared phi. So, let us do this. So, we have 2 kappa L del squared phi minus L times dou f 0 by dou phi, and dou f 0 by dou phi is nothing but A phi into 1 minus phi into 1 minus 2 phi, right. So, if you look at this equation, this is also looking like a diffusion equation, right. If you identify this like a constant, that is like diffusivity, then dou phi by dou t is some constant times del squared phi is the diffusion equation, but you have a term which is like a source term. So, this is also known as reaction diffusion equation, because when you write diffusion equation in cases where there are also reactions that some species form or consumed, then this is the type of diffusion equation that you would see. This is also a nonlinear diffusion equation, except that the nonlinearity is not in terms of del power 4 phi, but it is in terms of a polynomial that is added to this function. This now describes scenarios like the order disorder transformation that we are looking at. Okay. Now, all phase field models that we write, at least in solid phase transformations in material science, can be considered as combinations of Cahn-Hilliard equations and Allen-Cahn equations. So, we are going to look at several case studies as we go through the rest of this course, where we will take some specific problems like spinodal and ordering as the basic problems. Then we will take, say, precipitate growth or grain boundary grooving or grain growth and so on. And for example, grain growth will be modeled using Allen-Cahn equation, because in grain growth there is no mass conservation involved. You can start with 10 grains, at the end of the simulation you might end up with 2 grains. So, if you denote the grains using these kind of phi order parameters, then they are non-conserved order parameters, then the relevant equation that you have to write for their evolution is the Allen-Cahn equation. If you write composition, precipitate growth for example, in those cases the composition is the relevant order parameter and that is a conserved order parameter. So, Cahn-Hilliard equation is the right equation that you have to use. So, basically Cahn-Hilliard and Allen-Cahn put together is what all the phase field modeling is about with respect to microstructural evolution in material science and metallurgy. Okay. So, we are going to do that, but before we do that, let us take this Allen-Cahn equation and solve this numerically and look at the solution. So, that is what I will do in the next part of this lecture. Thank you.